So to conclude our talk of attractor landscapes, let's tie this together to the readings for this section of the course, which we will see in a few slides. Uh, but just dive straight to it and hope we get something out of it. So we're going to discuss the scope, state, resolution, and scale. Um, so in understanding the system. So you may have some sort of a temporal scope in the terms that uh, in the Ryan paper, emergence is coupled to scope, not level. And so the scope could be temporal or geographical. And the thing is that you might have some sort of a very micro level scope. So you would look at the system. Okay, so what does this person do in a week? Uh, um, and you would, or in during one day, or during 1 hour, and you might not see much of attractors or patterns or anything like this because you have a very small scope that you have used. But then if you would increase the scope of observation to include more people or a larger geographical area or a larger temporal span, so for example, months or something, or something like this, you might see that there is this single attractor where the system is laying in, and whenever it gets pushed around, it comes back. And then when you increase the temporal scope even more, you might see that there are actually these many different sort of states where the system can travel to. But you should, of course, if you have this map of an attractor landscape in your head, even at this point, you should start thinking that, hey, maybe I should think about what happens if uh, this situation is actually one where there are other attractors beyond what I'm looking at now. So even though I have only observed what I have observed now, it doesn't mean that something completely new and ridiculous could come about, or something very dangerous like a new pandemic, or the melting of polar caps launching new viruses and bacteria into the air, or something like this. And so what point is, when you increase the scope, you see this effect of the of emergence. And state and resolution. So the system has different states. So here you have the ball on the left, which is a different state than the ball lying in the bottom of the big attractor. So those are two states. But then when you blur out the resolution, you can see that, okay, so this landscape actually only has, with this resolution, if I only care about this uh, scale of observation, I only see 3 meaningful attractors. And but this blurring has a different effect, because in the previous picture you saw that, okay, so 2 attractors just disappeared. But if you were to blur out something like this, there wouldn't be much of an effect. It's the same thing. You still see 1 attractor, but then you might have something like this, um, and you blur it out, and it just becomes. It used to be very rich terrain, but now it just becomes a mode, like blur. You can't distinguish any information from there. And so the question that's sometimes asked is that, well, is my system complex or is it not complex? And this, of course, it depends on the resolution. If you had a look at the Ryan paper, so some systems are highly detailed, but when you blur them out, nothing remains. And you can think of the blurring effect in as you're looking at the screen. So if you would start blurring out the screen, the picture in the screen, how much detail would you keep on seeing? So this is sort of a line like this. So there's a lot of complexity on the low resolution or the high resolution or low scale, but not much elsewhere. And other systems, they're very coarse, but blurring out them has really no effect. So it might look like this, and other systems have structure on all resolutions, and you would see something like this. And I highly recommend you looking at the Siegenfeld and Baryam paper towards the end. They have a very nice explanation of this.